Yeah. Hello again. I'm Sergey. You might remember me from the morning presentation today. I'm still with Meta. We both are. So. Yeah, and in the morning I was talking about integrating our bindless Vulkan framework with esoteric UV samplers. Now we will do something more practical. So we will integrate the bindless stuff with ray tracing and just wrap it into a nice clean rendering API on top of Vulkan. Show some examples, what's possible to do with that. And more importantly, more interesting for you, there will be some performance information about how this stuff runs on mobile devices and compare some performance metrics across different popular devices. And Roman here will guide through the process. Just please go ahead, Roman, and share our stuff.
Thank you, Sergey. Hello, everyone. So, as Sergey announced, today will be more practical presentation in which we'll try to do some ray tracing in our LightweightVK. So, useful links before we start, like latest Vulkanized. It was a great presentation about realistic graphics on mobile devices. And that time, Sergey told me we should have it in the LightweightVK. And a year later, we have. In summer, Sergey did also a presentation about what actually Bindless is. I noticed from the first presentation that not all of you familiar with this concept. So I'll try to give some hints. Please feel free to ask us questions after this presentation if you're really interested in that. What goals of our work and this presentation? We want to demonstrate your practical approach. How to take Vulkan API related ray tracing and put into some umbrella API called LightweightVK. Small remark, LightweightVK, it's a fork of IGL library that Meta open source a couple of years ago. So LightweightVK, it's a fork in which we can do everything we want. It's like a sandbox for us to test new features, to go out of the box of what we cannot allow us to do immediately in IGL. So the second thing we want this running on mass market devices, something we can buy it at shop and everyone can do the same. So, and the first important thing, it should be open source, and it is open source. So during this presentation, you can go by this link and find all point code I will show to you, and you can compile it. I hope it will run. So anyway, that's the goal. And before we start, just short reminder what Bindless is. So in really simple words, when we are talking about Bindless, we do not bind every single resource when we do rendering, right? We access these resources in shaders. For buffers, we use pointers or physical buffer addresses to refer to different buffers in shaders. For textures, samplers, images, we use arrays and we use index to access these arrays in shaders again. So that scheme allows us to remove many things in CPU-hosted API and move a lot of things to shaders. And this concept is really natural for ray tracing. For ray tracing, we should access the whole geometry of the scene. We should access multiple shaders in shaders. So that's why this approach are really close to one to another. And what actually required if we want to add something like ray tracing to our API and want it to be enabled on Android devices. So this thing I got from Sasha's website, so it's quite representative. So you can see like ray tracing as a whole can be divided into two parts. It's ray query when we do some ray tracing feature in fragment shader and full ray tracing pipeline. So if you look at this slide, you see like about 7% of mass market Android device have acceleration structure and ray query. Acceleration structure is bare minimum, so it doesn't make any sense to have ray query without acceleration structure. So if you want to add something like that to your application, you unfortunately at the moment should target only to 7% of mass market devices. But I hope in time it will grow. The story is much worse for full ray tracing pipeline, less than 1%. But we still found some devices that are capable of doing it. So for full ray tracing pipeline, we used Samsung S24. So you can buy it, but there is a caveat here. If you buy Snapdragon version, this extension will be blocked for you. But what you need to do is buy European version, let's use Exynos, and it will be available for you there. Unfortunately, S25 reportedly will not have this thing. So if you want to buy a good device, you need to buy S24 now. For device, we compare at least ray query. We use Immortalis, Meli G715 device, like to compare with Samsung One. So what we actually added to LightweightVK. First of all, it's lightweight in the title, so we wanted to make it easy to get into any single Vulkan feature, including ray tracing. So for acceleration structures, we use handle-based approach that we used for all other stuff. You will see a bit later how it looks like. So this stuff allows us to easily manage lifecycle of objects, enable access to them, cast them to addresses or indices in case of textures and acceleration structure. So it's bare minimum for ray query. For full ray tracing pipeline, we need a bit more. We need to somehow master shader binding table. It's not really straightforward concept in ray tracing API in Vulkan. So for many users, I believe it's not really clear, but we try to make it as easy as possible. So we basically remove it from API from user. We just hide it inside LightweightVK. The same stuff connected to pipeline bindings, descriptor set updates, synchronization barriers, and all other interesting stuff that typically too overwhelming for users who never worked with Vulkan before, for example. So let's start going into some code, and I'll show you what handles are. So this is code from our sample from LightweightVK. As you can see, we create acceleration structure at bottom level in this case. So we return handle from it. By this handle, we can later access this acceleration structure. And as you can notice here, we use other handles, rise index buffer handle, transform buffer handle, vertex buffer handle to refer to other objects that related to this acceleration structure object. So you can see how we create them. So pretty much the same, like different handles for buffers that we used previously for built-in BLAS. So let's look inside how we convert it to Vulkan, usual Vulkan objects. So when we create BLAS, we fill big Vulkan structures, and as you can see, most important part, how we cast handle for vertex buffer into GPU address. So when we need this GPU address, we just cast it and get it. So users will not work with GPU address directly, only via handle for objects. Then we fill out this structure. We created some helper structures for acceleration. It includes useful information like link to buffer that actually owns it, fast link to device address. Other information requires us later to use them. So yeah, when we created acceleration structure, before we create acceleration structure, we need to build something that's called scratch buffer. Scratch buffer is some concept that additional memory for GPU to calculate acceleration structure. And important thing here, I highlighted with red, it's alignments. Alignments are everywhere. So when we use ray tracing, all addresses we use should be aligned by some value. For many for the devices we've seen, it's 256 bytes. So the thing we encountered when we started to use it, we need to override alignments for these structs. We typically use alignments that Vulkan returns us for different memory types, but for acceleration structure and other retracing objects, it can be different value. And another thing is VMA didn't work well if we pack in the same buffer other buffers with multiple alignments, multiple different alignments. So for that, we get rid of VMA for at least scratch buffers, acceleration structures, and allocated memory by ourselves. If you will not do it, you will get something like that. Now, finally, we create acceleration structure, we record its address, and we create handle for it, so you can use it later. But there is a problem. Actually, when you try to build this acceleration structure, you can potentially have overflow of storage buffers. For these two devices, we found interesting thing. For Mali, to build a scratch buffer, actually, Vulkan tells us your scratch buffer should be more than 7 gigabytes. That is, unfortunately, didn't fit into limitations for storage buffer. That's actually 256 megabytes for this device. So to build this acceleration structure, we should split our BLAS into about 30 parts. On the other hand, Samsung device didn't have a limitation for storage buffers, and for some reason, size of scratch buffer is about 570 megabytes, so it's much more reasonable than previous one. So if you try to do something like that, be ready that different devices can have different requirements for this part, and splitting BLAS into multiple parts should be essential part of your engine or framework if you're doing something like that for production. Now how we use top-level acceleration structure, the same way, again, handle, create buffer, really similar to BLAS. But there is a thing how TLAS different from BLAS. We should refer to TLAS from shaders. If you remember one of the first slides when we use textures and samplers in shaders, again, we use TLAS the same way. We have arrays of them, and we address them by index. In this example, you will see that we pass index of TLAS to shader using push constant, and later in RayGain shader, we use this index to get TLAS we want to have. Example from fragment shader, in what we use ray query extension. So the same way, we again pass array of TLAS, and actually the thing is that fragment shaders in this situation similar to RayGain shaders and other shaders make for us easy to pass these TLAS into shaders. For that, we just create a special set of descriptor for this array, the same way as we pass textures to Bindless rendering, we pass TLAS objects. As you see, to maintain index, the same index we use in CPU side and use it in GPU. We for BLAS we use first valid TLAS to fill this buffer and keep indices the same. Now how we actually do call ray tracing. We pass index of TLAS to shader using push constant. If we need to update TLAS in terms of we have something rotating, we call update TLAS. I will show you later how it looks like. We bind something we call a ray tracing pipeline. I will show how it looks like a bit later. And we just call ray trace. In LVK, we also have a fancy version when we pass texture to what we want to write output for that. To use it later, in this example, we copy this image to swap chain to render it immediately to the screen after finishing ray tracing. So how it looks like in LVK to run ray tracing. Ray tracing pipeline, as I promised, is pretty much everything what we have. We have 6 types of shaders. We limit how many shaders of these types we can have, and that pretty much it's your interface. So you just fill up this struct and use it. So this description will be split into multiple parts internally. So from it, we will generate a pipeline layout, all VK pipeline we need for rendering. We generate push constants mask to understand to what shaders, what set of shaders you use, and to what we need to pass some data. And most intriguing part, shader binding table, and most complex part. For shader binding table, we need something that's called groups. Groups, in my personal opinion, is not really simple concept in Vulkan API. So for groups, there are multiple rules. So ray gain shader, mist shader will form own groups. Any heat shaders will be connected to one group. So by our API, you will see how it looks like. We have one rain gauge shader, one heat shader, and 2 mist shaders to implement shadows. So in this example, we will split them into 4 groups. And all indices for this group will be calculated automatically by order of your shader in this struct. So in this example, you will see that in your shader, you need to call second ray and use another mist shader. It's a classic technique to implement shadows. So you use index 1 here, read in the example, exactly number of mist shader in this array. For heat and intersection shader, it's a bit more complex. You see from the Vulkan documentation how it's calculated in Vulkan. So depending on your setup, it can be index can be different. But in simple case, if your instance shader binding table record offset is 0 and shader binding table records right is 0, it can be the same as mist index. So again, indexing the array. Now, retracing pipeline state, our structs that allow to simplify for us internally render things. It contains all the stuff we should use when we call CMD trace race. So it includes regions to refer to our ray tracing shaders, link to shader binding table, and other useful things. And we use it like you can imagine. When we bind ray tracing pipeline, we first of all understand if this pipeline the same as previous one. If it's not, we will rebind pipeline associated with this ray tracing state, and we update descriptor sets for it. And after that, we can just call CMD ray trace and pass all regions we stored before to render to call ray tracing. Synchronization, interesting part. So for synchronization in LightweightVK, we have the concepts that call dependencies. It allows us to simplify dependency between different stages of your rendering pipeline. For ray tracing, we use the same concept again. So by dependency, for textures, we just wait until everything is ready. So we put all the barriers, all transition layouts automatically. For buffers, we do the same. And after that, when we can ensure that there is no any ongoing processes with this object, we can call ray trace and use them there. When we update top-level acceleration structures, again, this structure can be used on previous frames. So we can put some barriers that prevent us from accessing this data simultaneously, I mean, writing to them simultaneously with reading. So we insert all these barriers for you automatically, and it really simplifies way how you work with ray tracing. And for transitions layout, again, we use the same like we do for other type of rendering. It's like a huge verbose piece of code, so you can check out by this link if you are interested in that. So funny part, our demo in is mostly like, I would say it's like load test. It's not, it wasn't goal to optimize it just to make it this super efficient, but just to take a sense how it works on device. Is it possible to run it in some reasonable frame time or not? So some devices show excellent performance in this demo. It's ambient occlusion plus shadow rays. For 720p and for seeing this, like you I think you know what this scene is. Sponsor. So we got like 24 milliseconds. So it's impressive for a mobile device. For ray query. For more complex scene like Bistro, with 10 times more triangles, 2.8 millions. We got 220 milliseconds. What's not real-time performance, but it's still quite impressive just for your mobile phone. Much better for full ray tracing pipeline. In this scene, you see this scene doesn't have classic rasterization at all. Every pixel built by two rays, primary rays that actually build simple lighting, and secondary ray that do shadows. So for this device, we got 20 milliseconds. 12 milliseconds. Super impressive. For the even more impressive for me, for scene, we have 10 times more triangles. We have only 15 milliseconds. So it's not linear growth. It's like you can actually, your device can render such complex scene with not, and time is quite reasonable. So you can render something else. Instead of simple lighting, you can do much more sophisticated lighting in this situation. Unfortunately, device with Immortalis doesn't support full pipeline, so we can show it only for Samsung device. So, outcomes. First of all, we did it. So we have ray tracing is LightweightVK. So you can use it. It's open source. If you're thinking about using it for any production-ready software, please be aware that not too much devices can actually run this code, but some of them can, and some of them can do it really good. Yeah, it's end of my part. Sergey, you want to add something?
Thank you, Roman. So yeah, just again to emphasize, so all of this is already on GitHub. The ray tracing capabilities are in the master branch, and the mobile demos are as pull requests, so you can just take a look, build that stuff, and try to run it on your favorite devices. And again, we try to compare devices which are available actually on the market, and you can really just buy them and try the stuff we're doing here on your own. And I hope you find it useful. So thank you so much, and your questions.
I have a question regarding, because there's a very substantial speed difference between your primary rays, which I assume are basically primary, so they're coherent, and your AO plus ray trace shadow benchmark. And the very important implementation detail, which kind of interests me, is did you do the ray queries in a separate subpass, or did you do all 3 ray queries at once? Because I have a slight suspicion that the shadow rays could probably also be fast because they're coherent, but the GPU is probably screaming and crying because of all the cache misses.
That's the whole point, to make it screaming and crying. And I will actually confess. So this demo is actually calling ray queries for invisible pixels. So when we are doing this like overdraw, it's calling this for invisible pixels. And the whole point of the demo is just to do a relative comparison between different devices. So it's not an attempt to build any kind of like performant renderer and optimize anything, not at all. It's just a raw brute force benchmark between different devices with the only purpose to put them on their knees and just compare raw performance what is possible. And we see like 15x performance difference with between real actual production devices. And this is not something like in a different price range. All of those are flagships with their vendors. We're talking about Samsung, we're talking about Google devices. So no optimizations here, just an attempt to show the current state of the drivers and of the devices on different GPUs.
Thank you for your question.
Time for one more question, if there is one. Okay, we can thank our speakers.
Thank you.
Okay.